Time. It's time for function inverses with Mr. Dean. Let's get it on. Here we go. Finding inverses graphically is one way to do it. We'll also later be finding inverses algebraically. But if you have a graph, and that's all you have for the function, let's say we don't even know or care about the equation for this purple line over here, blue line on the left, what we can do to find the inverse of this function is just think that the way inverses work is they replace every x with y and every y with x. All that is switched. Inputs now become outputs, outputs become inputs. Everything is rearranged. So if I have a graph with coordinates on it, I can take each individual coordinate, each point, like that one, 0, 1, and on my new line, instead of 0, 1, my new line will have 1, 0, point at 1, 0. Or sorry, it's 0, 1. And instead of on the blue line a coordinate at 0, comma, -3, my inverse will be at -3, comma, 0. In fact, I don't have to worry just about x-intercepts or y-intercepts. I can take any point on the line, like 2, comma, 3, and now on my new line that will be 3, comma, 2. I can take a point like out here again, like 3, comma, 6. X is 3, y is 6, and just switch it around again. X is 6, y is 3, so that'll give me the corresponding point there. All right? And you will see as I try to draw a straight line through all that, sort of, you will see something kind of interesting about it. They are certainly not parallel, those two lines. They're not perpendicular either. So what would be sort of the relationship between those two lines? Well, there is sort of an invisible line of symmetry right down the middle. All right? And that line of symmetry has a equation y equals x. And that's literally what we're doing. We're switching the y's and x's, okay? So our blue kind of line, we'll just call that f of x. And our name for our green line then, the inverse of that, where all the domains are switched to ranges and all the ranges are switched to domains, is f with this little -1 as a sort of as an exponent. But as you know, just like with trig, that means inverse and doesn't mean flip it over like you would with exponents. Okay, so we don't really say f to the -1, we just say the inverse of function f. All right. Now on the right-hand side, we've removed all the coordinates. We don't have any numbers here, but that's not really hard. We'll go with our idea of, if we're going to draw the graph of the inverse of that green graph, then we draw a graph that is a mirror, kind of mirror images over that blue line. A little harder for some people. I'm not very good at it. I do know where they cross, right there and right here, are going to be in common, because those are the points where x and y are equal for the graph. All right? And now I'm going to try to complete the graph, and we're not going to go coordinate by coordinate, of course. We don't have any numbers. I'm going to try. There we go. Kind of missed that one. Well, okay. Not too shabby. And we have a couple of things in common here. On the green graph, we had a point right there, and I just sort of try to mimic that point on the y-axis, all right? Anything on the x-axis becomes on the y, and that point over here is approximately the inverse of that, not bad. And that blue, again, that blue dashed line doesn't really exist. It's just used as a symmetry line, all right? So the green graph, again, that would be our original function, f of x, and our black line would be the inverse. So you can draw it without coordinates, not too bad. Now, once we start talking about inverses, some functions actually have inverses and some don't. So a function that has an inverse only if it is 1 to 1, all right? So that's sort of a new phrase, 1 to 1. What that means is every output has just one input, all right? Get that straight, because a function, just for something to be a function, it has to have one input for every output. Now we're saying it the other way around, the inverse of it. We're saying for it to be 1 to 1, for a function to even have an inverse, each output has to have only one input. And graphically, it's very easy to tell if something has an inverse because you use the horizontal line test, the HLT, and it's used to tell if a function has an inverse. And not all of them do. Not all of them do. So, like, well, we'll get right into some examples, I suppose. Let's do that. There's your example of an HLT. Do these functions have an inverse? All right, so write down these 6 equations, these 6 graphs now. You might want to pause the video and see if you can actually just do little sketches of the graphs right now. Okay, so pause the video and we'll come back in a second. The graph of each of these looks like this. These aren't super accurate, but they're the best I could do. All right, and that one goes down a little bit there. And the horizontal line test, really easy. What you do is you take a good old horizontal line, just like the vertical line test. The vertical line test tells whether something is a function or not. The horizontal line test tells me that this does not have an inverse. It is a function, but does not have an inverse. Y equals x squared doesn't really have one inverse. If I told you I'm thinking of a number, and when you square it, you get 16, you don't know whether I'm talking about, say, -4 or +4 to get 16. So it doesn't have an inverse. Same thing goes with absolute value. There's no inverse to absolute value. There's no symbol that takes care of that at all. But with square roots, yeah, you can have an inverse of a square root. Does have an inverse function. It's the squaring function. Now, things get really complicated with trig, with sine and cosine especially. It appears as though the sine wave does not pass the horizontal line test, and it doesn't. Right? There's many different values. It really doesn't. But inverse sine, there is an inverse sine. It's right on your calculator. There's an inverse sine button, and you're going to use inverse sine quite a bit in trigonometry. So why is that? How is that? What the heck happened? Well, we kind of artificially define inverse sine to only look between -90 degrees and 90 degrees, or -π/2 and π/2. And if we sort of just ignore this other part and say, don't look there, don't look over here either, then it passes the horizontal line test. Okay, so that's kind of a special case. And very similar, but slightly different with cosine. Cosine moves over to 0 to 180, but either way, they do have inverses. All right. Now, how about y equals 3? Kind of interesting idea. Clearly, it totally fails the horizontal line test. There's no inverse of 3. And if you have a cube root or anything to an odd power, it is going to pass the horizontal line test. But don't be too confused. If you did have something like, if I gotta change this, y equals some amount of x cubes, and then you have a more complicated expression in between, you'd have to take a look at the graph on your calculator, because this graph might end up bumping, and if it bumps, it would not pass the horizontal line test, meaning that there's no inverse. All right, now, that's graphs. Finding inverses algebraically. We're going to use a technique known for thousands of years as the switcheroonie, or the old switcheroo as a nickname technique. And here we have a function f of x equals 3x plus 8. We are going to switcheroo, as I sort of alluded to earlier in the video. All our x's are y's, all our y's are x's. All right? So first, we're going to take our f of x equals 3x plus 8. And instead of f of x, I'm going to replace that with y. And we haven't done anything strange yet. F of x is just another way of saying y. And then I'm going to do my switcheroonie. I'm going to switch them. Everywhere I see x, I'm going to put y. Everywhere I see y, I'm going to put x. And then I solve for y and get y all by itself. So in this case, it's a two-step process. I'm going to subtract 8 on both sides, and then I'm going to divide by 3. So I get x minus 8 equals 3y. And finally divide by that 3 there. And you're going to have y equals x minus 8 divided by 3. And we want to label that as our inverse. We found it. So our inverse function is written like that. That's our inverse. Now that's a two-step process. That wasn't too bad. If you do get confused, there is this idea of an arrow diagram where You take your function, and it may be a multi-step, kind of more complicated function, and you write x, and then you write in each arrow what is being done to x. First step is times 3, the next step is times 8, and that will get you y. And then in the backwards arrow, you simply reverse your steps, take the inverse operation, and this will tell you what to do. We switcheroonie the x and y's, and we get that y is equal to, start over here on the right, x, follow the arrows, minus 8, follow the arrows, divide by 3. Either way, you're going to get the inverse function correct. All right? Now, one thing about inverses is that it's the opposite of operation and the opposite order. And that kind of can sometimes be hard to keep track of. Let's do one that's 3 steps at least here. Try this one right now if you'd like. We'll go over it together. Square root of 2x minus 5. So the first step is I'm going to change this to y. And then I'm going to do the full switcheroonie of x's with y's. Now in my arrow diagram idea, the first thing that's done to x in blue is multiply by 2, and then they're subtracting 5, and lastly they're taking the square root. So reverse that. The first thing we want to do is do the inverse of square rooting, which is squaring. But that's what I'm going to do over here on the right-hand side to my red equation. I'm going to square both sides. And if I square this side, that'll get rid of the square root. I don't know if I can erase it quite clearly here, but pretty good. Now I just add 5, and I have x squared plus 5 equals 2y. And then clearly, last thing I do is divide by 2. So that my function inverse is x squared plus 5 over 2. All right, so you see that last challenge at the bottom there? Let's go through that one. Really not too much harder, though. I'm going to change h of x, doesn't really matter what the name of it is. I'm going to change it to y, and then I'm going to switch my x and y's. So we get the cube root. I don't do a lot of work with the cube root, but let's try this out. So the first thing I want to do is add the 7, because that 7 is not underneath the old hat of the cube root. So that's a separate function, a separate operation. We'll take care of that first. We have x plus 7 equals the cube root of y. Remember, we're solving for y. And to get rid of the cube root, we simply cube. We cube both sides. And so our inverse function is equal to the entirety of x plus 7 in parentheses. That was first. Then that gets cubed. All right? So that is function inverses, both graphically and algebraically. That was a quick one. Hope you had a great time watching, and we'll see you in class.